Right now, there is a spacecraft so far from Earth that if its computer crashed, the engineers in California would not even know for almost 24 hours. And when they sent a fix, it would take another 24 hours to arrive. For 2 full days, that machine would be alone with its malfunction, drifting through interstellar space with no one able to help. That spacecraft is Voyager 1, and it is only about 1 light day away. That is practically next door in cosmic terms. The truly terrifying thing about deep space is not that something dramatic is waiting out there to kill you. It is that with every mile you travel farther from Earth, you lose something you depend on. Sunlight, communication, rescue, repair, warmth, and eventually, hope of return. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. 250 miles. That is how far the International Space Station orbits above the surface of the Earth. If you could drive straight up at highway speed, you would be there in under 5 hours. It is, by any cosmic standard, absurdly close. And that closeness is not a minor convenience. It is the single reason the station works at all. For more than a quarter century, human beings have lived and worked aboard that station. More than 270 people from over 20 countries have floated through its modules, conducted thousands of experiments, repaired aging equipment, grown food in miniature greenhouses, and exercised for 2 hours every single day to slow the bone loss that weightlessness inflicts on the human skeleton. They have watched hurricanes form below them, seen the aurora shimmer in green ribbons over the poles, and photographed the thin blue line of atmosphere that separates everything alive from everything that is not. And during all of that time, across all of those years and all of those crews, one fact has quietly underpinned every success and every survival. Earth was right there. When an astronaut on the station speaks to Mission Control in Houston, the signal travels at the speed of light and arrives in a fraction of a second. The delay is so small, it is undetectable in normal conversation. You talk, they hear you, they respond, you hear them. It feels no different from a phone call, and that immediacy is not a luxury. It is a survival mechanism. If a fire breaks out on the station, and fires have broken out on the station, the crew can report it and receive guidance almost instantly. If a cooling loop fails, if a pressure seal degrades, if an ammonia leak contaminates the air supply, engineers on the ground can pull up schematics, examine telemetry in real time, and walk the crew through a repair procedure step by step while the crisis is still unfolding. In February of 1997, a solid fuel oxygen generator aboard the Russian space station Mir caught fire and burned for approximately 14 minutes. The fire filled the station with thick, acrid smoke. It partially blocked the corridor leading to one of the 2 Soyuz escape capsules, which meant that 3 of the 6 crew members were temporarily cut off from their only way home. They could not reach the vehicle that was supposed to save their lives. The crew extinguished the fire using onboard equipment, but the incident revealed something critical about emergencies in space. There is no fire department. There are no first responders outside the hull. The crew must handle the situation themselves, in the moment, with whatever tools and training they have. On Mir, they succeeded because they had practiced extensively, because the suppression equipment worked, and because the station was close enough to Earth that continuous communication with the ground was possible throughout the crisis. Mission Control could hear every report. They could see every reading. They could advise in real time. That connection mattered. The International Space Station inherited those lessons. Its fire suppression systems are more advanced. Its crew training is more rigorous and more scenario-specific. Its escape vehicles are more capable. And critically, there is always at least one return vehicle docked at the station, ready to bring the crew home at a moment's notice. In the current era, that is typically a SpaceX Crew Dragon capsule, sometimes supplemented by a Russian Soyuz. If the station becomes uninhabitable, if something goes so fundamentally wrong that it cannot be fixed or contained, the crew climbs into the return vehicle, undocks, and in roughly 3.5 hours, they are on the ground. 3.5 hours from a crisis in orbit, to solid Earth beneath their feet, to ambulances and medical teams and breathable air that does not come from a machine. Resupply is equally routine. Cargo vehicles arrive at the station every few weeks, carrying food, water, equipment, replacement parts, scientific instruments, personal items for the crew, even fresh fruit. The supply chain between Earth and low Earth orbit is one of the most reliable logistics operations humanity has ever maintained. Multiple launch providers from multiple countries rotate missions so regularly that the arrival of a cargo vehicle at the station barely makes the news anymore. If a critical component breaks, a replacement can be manufactured on the ground, tested, loaded onto a rocket, and delivered to orbit within a matter of weeks. The crew never has to wonder whether help is coming. It is always coming. That certainty is woven into every operational decision, every maintenance schedule, every risk assessment that the station's managers make. They plan with the confidence that Earth is a dependable partner, available around the clock, seconds away by radio, weeks away by rocket. Now consider what all of this adds up to. At 250 miles altitude, an astronaut has real-time voice and video communication with hundreds of engineers and scientists on the ground. Immediate access to expert guidance in any emergency, regular deliveries of supplies, spare parts, and consumables. A vehicle standing by at all times that can return them to Earth's surface in hours. Medical support that is effectively limitless, because the full infrastructure of terrestrial hospitals, specialist physicians, and pharmaceutical supply chains is only a radio call away. If everything goes irreparably wrong, they can evacuate. They can come home. That option is always on the table. The International Space Station is routinely and accurately described as one of the most dangerous workplaces in existence. The vacuum outside the hole will kill an unprotected human being in roughly 90 seconds. Micrometeoroids strike the station's exterior on a regular basis. In 2016, a tiny particle, probably smaller than a flake of paint, struck one of the station's cupola windows and left a chip about 7 millimeters across. That particle was almost certainly traveling at several miles per second relative to the station. At those velocities, something smaller than a grain of sand hits like a bullet. Larger particles, the ones big enough to penetrate the hole, are tracked by radar from the ground, and the station periodically fires its thrusters to maneuver out of the way. These debris avoidance maneuvers happen several times a year, but the small particles, the ones too tiny to track, arrive unannounced. The station's hull includes Whipple shielding, layered bumper plates designed to shatter and disperse incoming particles before they can reach the inner pressure wall. The shielding works well for particles below a certain size threshold, but over the station's operational lifetime, the cumulative pitting and micro damage to its exterior surfaces accumulates quietly, a reminder that space is not passive. It does not simply surround you, It acts on you, constantly, in ways that compound over time. Radiation is another constant. The station orbits inside Earth's magnetosphere, the vast magnetic bubble generated by the planet's churning liquid iron core. The magnetosphere deflects the majority of charged particles streaming through the solar system, including protons from the solar wind, energetic particles from solar flares, and the high-energy nuclei of galactic cosmic rays. Inside this shield, astronauts are partially protected. They still receive significantly more radiation than people on the ground, because the station orbits above most of the atmosphere. And there is a region called the South Atlantic Anomaly, where the inner Van Allen radiation belt dips unusually close to Earth's surface, creating a zone of elevated radiation that the station passes through multiple times per day. Over a 6-month tour, a station astronaut accumulates a total radiation dose many times higher than what a person on Earth would receive in a year, contributing to a measurable, long-term increase in cancer risk. But it is not acute. It does not cause radiation sickness. It does not impair cognitive function during the mission. It is a managed, monitored, accepted risk, understood by every crew member before they fly. Every threat the station faces, every danger, every close call, every repair, every emergency exists inside a safety envelope defined entirely by one variable: proximity to Earth. The station is close enough that communication is instantaneous, close enough that resupply is routine, close enough that evacuation takes hours, close enough that Earth's magnetic field provides meaningful radiation shielding, close enough that the full weight of human civilization, its engineers, its physicians, its supply chains, its collective expertise, can be brought to bear on any problem the crew encounters, in real time, while the problem is still happening. Remove that proximity and everything changes. Not the types of threats. Space is hostile everywhere. What changes is the ability to respond. And that ability depends on distance more than any other single factor in the entire equation of survival. Let us move to the moon. The moon sits roughly 240,000 miles from Earth. In cosmic terms, that is still close. Light covers that distance in about 1.3 seconds. A radio signal from the lunar surface reaches Houston so quickly that a conversation feels almost normal. There is a faint pause, a subtle lag, but nothing that disrupts the flow of information. You can ask a question and get an answer within 3 seconds. You can report an emergency and receive instructions almost immediately. The communication part is manageable, but rescue is not. The fastest any crewed spacecraft has ever traveled to the moon took approximately 3 days. The Apollo missions of the late 1960s and early 1970s flew trajectories that placed the crew in transit for roughly 72 hours each way, sometimes a bit more, sometimes a bit less, depending on the specific mission profile and the orbital mechanics of the departure window. 3 days is not a long journey by terrestrial standards. People spend longer than that on cross-country drives. But in the context of an emergency, 3 days is an eternity. If something goes catastrophically wrong on the lunar surface, or in lunar orbit, or anywhere along the transit corridor between the Earth and the Moon, there is no rapid evacuation. There is no ambulance. There is no rescue vehicle on standby that can sprint to the crew's location in hours. There is only the crew, their spacecraft, and whatever resources they carry with them. Help from Earth, if it comes at all, arrives slowly, and in practice, a rescue mission launched from Earth in response to a lunar emergency would take far longer than 3 days to arrive, because you cannot keep a fully fueled, fully crewed rocket on the launch pad indefinitely, waiting for a crisis that may never come. Launch preparation takes weeks at minimum. By the time a rescue vehicle could realistically be dispatched, the crew at the moon would have already survived or not, using only what they had. This is not a hypothetical concern. It is a demonstrated one. On April 13th, 1970, at approximately 55 hours and 54 minutes into the mission, the crew of Apollo 13 heard a loud bang reverberate through the spacecraft. An oxygen tank in the service module had exploded. The blast ruptured a second oxygen tank, disabled 2 of the 3 fuel cells that provided electrical power, and began venting the command module's breathable oxygen supply into the vacuum of space. The crew watched their oxygen pressure gauges drop. Within 2 hours, the situation was clear. The command module was dying. Its power was failing. Its oxygen was leaking away. The crew had to abandon it entirely, powering it down to preserve the small amount of battery life remaining for the re-entry sequence that would come days later, and retreat into the lunar module, a spacecraft originally designed to carry 2 people for roughly 45 hours on the surface of the moon. Now it was being asked to keep 3 people alive for approximately 90 hours in the deep cold of space, while the crippled vehicle looped around the far side of the moon and fell back toward Earth on a free return trajectory. The next 4 days were a continuous improvisation against narrowing margins. The crew rationed water so severely that all 3 men became clinically dehydrated. Mission Commander Jim Lovell later estimated that each astronaut consumed only about 6 ounces of water per day, roughly a fifth of the minimum recommended intake. The cabin temperature dropped below 40 degrees Fahrenheit because nearly every electrical system had been shut down to conserve power, and electrical systems generate heat. Condensation formed on the walls, the instrument panels, the windows. Fred Hayes developed a urinary tract infection from the dehydration. Jack Swigert had to help construct an improvised carbon dioxide scrubber using cardboard, plastic bags, and duct tape, because the command module's lithium hydroxide canisters were square, while the lunar module system was designed for cylindrical ones. The 2 shapes were incompatible. They were never designed to work together. The engineers in Houston designed the adapter on the ground, built a working prototype using only materials they knew existed aboard the spacecraft, tested it, and then read the construction instructions to the crew over the radio, step by step, while the carbon dioxide levels climbed toward dangerous concentrations. And here is the part of this story that matters most for the journey we are taking tonight. The crew of Apollo 13 survived for one reason above all others. Earth was close enough to help. The communication delay was only 1.3 seconds each way. The engineers in Houston could see telemetry from the spacecraft in real time. They could talk to the crew, hear their reports, understand their situation, and respond within seconds. The flight controllers worked in continuous shift around the clock, running simulations, testing procedures, calculating power budgets and trajectory corrections and re-entry angles, and relaying every solution to the crew as fast as they developed it. The rescue of Apollo 13 was a masterwork of real-time collaboration between a crew in mortal danger and a ground team with the full resources of NASA working at full capacity. Now, hold that story in your mind, because we are going to return to it as the distances grow. What made Apollo 13 survivable was not just the brilliance and composure of the people involved, though both were extraordinary. It was the physical fact that the people on the ground could participate in the emergency as it unfolded. They could see the problem developing. They could talk to the crew and hear the responses. They could propose solutions, receive feedback, refine their approach, and iterate, all within seconds. That capability is a direct function of distance. At the Moon, it works. At Mars, it does not. And beyond Mars, it ceases to exist entirely. In April of 2026, NASA launched Artemis Two, sending 4 astronauts around the Moon aboard the Orion spacecraft. It was the first time human beings had traveled beyond low Earth orbit since Apollo 17 in December of 1972. More than 53 years between crewed flights to deep space. Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen rode the Space Launch System rocket off the pad at Kennedy Space Center and into a 10-day trajectory that carried them around the far side of the Moon and back to Earth. The mission covered approximately 694,000 miles. And during those 10 days, those 4 astronauts experienced something that no living human being had felt in more than half a century. They left the protective magnetic envelope of the Earth. This is the detail that transforms the Moon from a familiar destination into a fundamentally different kind of environment. Earth's magnetosphere, generated by convective currents in the planet's molten iron core, extends tens of thousands of miles into space and forms a vast shield that deflects the majority of high-energy charged particles streaming through the solar system. Inside this shield, astronauts receive elevated but manageable radiation doses. Outside this shield, everything changes, and the boundary is not gradual. The transition from magnetically shielded space to unshielded deep space happens over a relatively narrow band of altitude. Once you're through it, you are exposed. Artemis Two carried instruments specifically designed to measure the radiation environment beyond Earth's magnetic protection. The crew passed through the Van Allen belts, 2 nested regions of trapped energetic particles that encircle the Earth like invisible donuts. The inner belt, concentrated between roughly 600 and several thousand miles above the surface, is dense with high-energy protons. The outer belt, extending from approximately 12,000 to 25,000 miles altitude, contains mostly relativistic electrons. Spacecraft trajectories are designed to transit these belts quickly, passing through the thinnest sections to minimize exposure. Beyond the Van Allen belts, the Artemis Two crew entered the unshielded deep space radiation environment. 3 overlapping threats, each with different characteristics, none of them fully solvable with current technology. First, galactic cosmic rays. These are the most persistent and the hardest to stop. They are high-energy particles, mostly protons, but also heavier atomic nuclei including helium, carbon, oxygen, silicon, and iron, accelerated to nearly the speed of light by supernova explosions and other violent astrophysical events across the galaxy. They come from every direction. They never stop. And they carry so much energy per particle that they can penetrate meters of solid material. A spacecraft hull measured in centimeters of aluminum does not stop them. It slows some, it fragments others, producing secondary showers of radiation that can be as biologically damaging as the original particle. There is no practical shielding thickness that eliminates galactic cosmic ray exposure without making the vehicle too heavy to launch. Second, solar particle events. The sun periodically erupts with flares and coronal mass ejections that blast intense streams of high-energy protons into interplanetary space. These events are unpredictable in their timing and severity. They can last hours or days, and if a crew happens to be outside Earth's magnetosphere when a major event occurs, the radiation dose can spike to dangerous levels in a matter of hours. Inside the magnetosphere, Earth's magnetic field redirects most of these particles harmlessly around the planet. Outside it, the spacecraft hull is the only barrier, and for a severe event, it may not be enough. Third, any airless body with a solid surface, like the Moon, generates its own secondary radiation hazard. When galactic cosmic rays and solar protons strike the lunar regolith, they interact with the rock and produce neutrons and other secondary particles that scatter in all directions. An astronaut standing on the Moon is irradiated from above by the primary deep space environment, and from below by secondary particles generated in the ground beneath their feet. There is no direction from which radiation is not arriving. The data from Artemis Two confirmed what decades of robotic measurements and physics models had predicted. Beyond Earth's magnetic field, the radiation environment is substantially more intense, more complex, and more persistent than anything astronauts experience in low Earth orbit. For a 10-day lunar flyby, the cumulative dose is elevated but tolerable. The crew returned safely. But the measurements underscored a sobering arithmetic that NASA's radiation biologists have been refining for years. The longer you remain outside the magnetosphere, the higher the cumulative dose, and the farther you travel from Earth, the longer you are exposed. A 10-day mission accumulates a manageable total. A 6-month mission accumulates something much more significant. A multi-year mission to the outer solar system would push cumulative exposure into territory where long-term health consequences become not just possible, but likely. And this is the thread that runs through everything we have covered so far. At 250 miles in low Earth orbit, you have instantaneous communication, rapid evacuation measured in hours, routine resupply, meaningful magnetic shielding, and the full real-time support of Earth's infrastructure. At 240,000 miles at the Moon, you still have near instantaneous communication, and some of those safety margins remain. But rescue stretches from hours to days. Resupply becomes infrequent and expensive rather than routine. You are fully exposed to the deep space radiation environment for the duration of the mission. Earth can still help, but the help is slower, less complete, and more conditional than it was in low Earth orbit. The tether between you and home is stretching. And if you have been paying attention, you can already feel what happens when it stretches further. Because everything we have described so far, the 3-day rescue timeline at the Moon, the 1.3-second communication delay, the brief radiation exposure of a 10-day mission, all of it exists within a distance that is, in solar system terms, barely a step from the front door. The Moon is close. It is the closest destination there is beyond Earth orbit. And even at the Moon, the safety margins are already thinner than most people realize. Apollo 13 survived by the narrowest of margins at 240,000 miles. A few degrees of re-entry angle, a few ounces of remaining water, a few hours of battery life. Those margins were razor thin, and they were only available because Earth was close enough to reach back. Mars is not 240,000 miles away. Mars, at its closest approach, sits approximately 34 million miles from Earth. At its farthest, it is over 250 million miles away. The distance to Mars does not simply scale up the same challenges the Moon presents. It introduces entirely new ones. The communication delay alone transforms the relationship between a crew and mission control from a real-time partnership into something more like an exchange of letters between people who can no longer see each other's situation. And the rescue window does not stretch from days to weeks. It effectively closes. It ceases to exist as a meaningful operational concept. That is where we are going next. To the distance where Earth stops being a safety net and becomes a delayed voice, speaking from the past, arriving too late to change what has already happened. Imagine you are a surgeon. You are standing over a patient in an operating room, scalpel in hand, and the patient's condition is deteriorating. You need guidance from a specialist. You radio the specialist and describe the situation. Then you wait. 4 minutes, 6 minutes, 8 minutes. The specialist has not responded because your message has not arrived yet. It is still traveling, moving at the speed of light across a gulf so wide that even light needs time to cross it. By the time the specialist hears your description, the patient's condition has already changed. By the time you receive the specialist's advice, which must also travel back across that same gulf, up to 22 minutes may have passed since you first asked the question. The advice you finally hear is based on a situation that no longer exists. The patient is different now, the readings are different, the crisis has evolved, and the specialist's next response, based on whatever update you send next, will arrive just as late. That is what communication with Earth looks like from Mars. The distance between Earth and Mars is not fixed. Both planets orbit the Sun, but at different speeds and different distances. Earth orbits at roughly 93 million miles from the Sun, completing one lap every 365 days. Mars orbits farther out, at roughly 142 million miles, taking about 687 Earth days to complete one orbit. At the closest possible approach, called opposition, when Earth and Mars are on the same side of the Sun, with Earth between Mars and the Sun, the gap narrows to roughly 34 million miles. At the farthest separation, called conjunction, when the Sun sits directly between the two planets, the distance stretches past 250 million miles. This fluctuation is not a minor detail. It determines everything about how missions to Mars are planned, launched, and operated. A one-way radio signal, traveling at the speed of light, takes approximately 3 minutes to cross the gap at closest approach. At the average distance, roughly 140 million miles, the delay stretches to about 12.5 minutes each way. At conjunction, when Mars is on the far side of the Sun, the one-way delay can exceed 22 minutes. And during conjunction itself, for roughly 2 weeks, communication is effectively impossible because the Sun's radio emissions drown out the signal entirely. The spacecraft is not just delayed, it is unreachable. Whatever is on Mars receives no commands and sends no usable data to Earth. It is alone. Let those numbers settle in. At the best possible moment, when the planets are as close as they ever get, a simple exchange takes 6 minutes. You ask a question, 3 minutes pass. Earth hears the question. They compose a response. 3 minutes pass. You hear the answer. In the average case, that loop stretches to 25 minutes. In the worst case, it is 44 minutes, or the signal does not get through at all. This is not the 1.3 second delay at the Moon, where conversations feel nearly normal and mission control can guide a crew through a crisis in real time. This is a delay long enough that by the time you receive a response, you may have already been forced to act without it. The fundamental dynamic of spaceflight, the partnership between crew and ground, breaks down. Earth does not become useless, it becomes historical. Every piece of advice that arrives from Houston describes a situation that existed minutes or tens of minutes ago. Every command that reaches the spacecraft was drafted based on information that is already outdated. NASA already lives with this problem every day, right now, on the surface of Mars. The Perseverance rover, which landed in Jezero Crater in February of 2021, does not operate in real time. No Mars rover ever has. The communication delay makes joystick driving impossible. Instead, mission controllers at the Jet Propulsion Laboratory in California upload a complete set of instructions each Martian morning. The rover receives the plan, executes it autonomously throughout the day, and transmits its results back to Earth in the evening. The controllers review the data overnight, draft the next day's instructions, and send them back. It is a system of daily dispatches, not conversation. And it works well for a rover, because a rover can be programmed to stop and wait if it encounters something unexpected. It has onboard hazard avoidance cameras and software that lets it navigate around obstacles without human input. If something confuses it, it simply stops moving and sends a photograph to Earth, then waits patiently for new instructions to arrive the next day. A human crew cannot operate this way. Humans do not stop and wait for a day when a medical emergency erupts. They do not pause and transmit a photograph when a fire alarm sounds. They do not put a surgery on hold for 25 minutes while they wait for the response to a question about where to make the incision. The communication delay at Mars does not merely slow the conversation between crew and ground. It fundamentally changes what mission control can contribute to the mission. At Mars distance, mission control can provide strategic advice, long-term planning, analysis of data that the crew sends back, moral support, and scheduled consultations on non-urgent matters. What it cannot provide is real-time emergency guidance. The crew has to handle crises themselves, in the moment, with whatever expertise and equipment they carry. And they have to make decisions knowing that if they are wrong, they will not learn about their mistake from Earth for at least 6 minutes, and quite possibly not for half an hour. This transforms crew selection in a fundamental way. A crew going to the moon can include specialists who are good at following precise instructions from the ground. A crew going to Mars must be composed of people who can function as an autonomous unit, making complex medical, engineering, and operational decisions without outside input. They need at least one person, and probably more than one, who can perform surgery, not elective surgery, emergency surgery, appendectomies, fracture repairs, management of internal bleeding, treatment of severe burns. Because if a crew member develops acute appendicitis on Mars, there is no helicopter evacuation to a trauma center. There is no emergency room. There is a crew medical officer with limited surgical equipment, limited pharmaceuticals, and limited experience, performing an operation inside a habitat on another planet, while the nearest hospital is at minimum 34 million miles away, and cannot offer real-time advice. Studies conducted by NASA's Human Research Program have examined this scenario in detail. The probability of a serious medical event occurring during a long-duration Mars mission, typically estimated at 2.5 to 3 years round trip, is not trivial. Over 3 years, in a crew of 4 to 6 people, the cumulative probability of at least one crew member experiencing a condition requiring surgical intervention has been estimated as several percent. That includes appendicitis, kidney stones requiring intervention, dental abscesses, traumatic injuries from equipment failures, or falls in reduced gravity, and a range of other conditions that would be routine emergencies on Earth, but become potential mission-ending crises on Mars. Pharmaceutical supplies are another concern. Many medications degrade over time, especially when exposed to the radiation environment of deep space. Some drugs lose significant potency within 12 to 18 months. A mission lasting 3 years cannot rely on medications that were manufactured and packaged before launch without understanding exactly how storage in a high radiation, variable temperature environment affects their chemistry. Research is ongoing, but not all results are reassuring, and the medical isolation is compounded by a second form of isolation that is just as operationally significant: launch window dependency. Earth and Mars align for efficient transfer trajectories approximately every 26 months. This alignment, governed by the orbital mechanics of two planets moving at different speeds around the Sun, creates a window of roughly 2 to 4 weeks, during which a spacecraft can depart Earth and reach Mars using a reasonable amount of fuel. Miss that window and you wait over 2 years for the next one. There is no accelerating the planets into a more convenient alignment. Orbital mechanics does not negotiate. For a crewed Mars mission, this means the entire logistics chain, every kilogram of food, water, spare parts, medical supplies, habitat modules, power systems, and return propellant must either be pre-positioned on Mars by robotic cargo missions launched during earlier windows, or carried by the crew themselves. There is no emergency resupply. If the crew discovers after landing that a critical piece of equipment was damaged during transit, or that a food production system is not functioning as expected, or that they underestimated how much of a particular consumable they would need, there is nothing Earth can do about it until the next launch window opens, more than 2 years later. And even then, the resupply mission takes 6 to 9 months to arrive after launch. So the effective wait time for emergency supplies is not 26 months. It is 26 months, plus the transit time, which brings the total closer to 3 years. This is a category of danger that does not exist anywhere closer to Earth. On the International Space Station, if something runs out or breaks, a replacement can be sent within weeks. At the Moon, resupply is difficult and expensive, but theoretically possible at any time if the need is desperate enough. At Mars, resupply is governed by celestial mechanics, and celestial mechanics is indifferent to urgency. You can run out of a critical medication on the first day of a 26-month gap between launch windows, and Earth can do nothing except send instructions for improvisation and wait for the planets to align again. The psychology of this isolation deserves careful attention, because it operates differently from any form of isolation humans have experienced before. Submarine crews are isolated for months, but they know the submarine can surface. Antarctic winter overcrews endure months of darkness and confinement, but they know the supply plane returns in spring. Even the crew of the International Space Station, while orbiting in the vacuum of space, can see Earth filling their windows, enormous and blue and close, a constant visual reminder that home is right there. They can call their families, they can watch live television, they can feel connected to the planet below in a visceral, immediate way. A crew on Mars has none of that. Earth, from the Martian surface, is a small bright point of light in the sky. It does not fill any window. It does not look like home. It looks like a star. And the messages from that star arrive with a delay that makes real-time conversation impossible. You can record a video for your family and send it to Earth, and then wait between 25 and 44 minutes for their reply. That reply will be another recorded video, spoken by people who are responding to words you said half an hour ago or more. It is an exchange of time-shifted monologues, not a conversation. You cannot hear your child laugh in real time. You cannot see the expression on your partner's face as they react to what you are saying in the moment you say it. The emotional connection that real-time communication provides. The sense that someone is right there with you, listening, reacting, present, is replaced by something that feels more like correspondence. Meaningful, valued, important, but fundamentally different. And over months and years, that difference wears on people in ways that are difficult to predict and harder to mitigate. NASA studied long-duration isolation extensively during the one-year mission aboard the International Space Station in 2015 and 2016, when astronaut Scott Kelly and cosmonaut Mikhail Kornienko spent 340 consecutive days in orbit. The results were sobering. Both crew members showed measurable changes in cognitive performance, immune function, gut microbiome composition, gene expression, and vision over the course of the year. Scott Kelly's identical twin brother Mark, also a NASA astronaut but remaining on Earth, served as a control subject for biological comparison. The twin study revealed that some of the changes Scott experienced in orbit were reversible after return to Earth, but others persisted for months. And that was a single year in low Earth orbit, with real-time communication available at all times, regular crew rotations, and the constant psychological comfort of seeing Earth just 250 miles below. A Mars mission would last roughly 2.5 to 3 years. The crew would be farther from Earth than any human has ever been. They would be unable to have a real-time conversation with anyone outside the spacecraft for the entire duration. They would be unable to return home if they changed their minds, if they became ill, if they became psychologically distressed. The return window is as constrained as the departure window. You launch to Mars during one window. You stay on the surface for roughly 18 months, waiting for the next alignment. Then you launch home during the return window. If you miss the return window, you wait another 26 months. The schedule is dictated by the planets, and it does not bend. There was a concept in psychology called the third quarter phenomenon. Researchers studying isolated groups consistently observe that morale and psychological well-being tend to decline most sharply around the three-quarter mark of a mission, the point at which the novelty has long since faded. The end is approaching, but not yet close enough to provide motivational lift, and accumulated fatigue and interpersonal friction reach their peak. For Antarctic winter-over crews, this corresponds to roughly the 7th or 8th month of a 9-month isolation period. For a Mars crew, the three-quarter point falls somewhere during the long wait on the Martian surface, months after landing and months before departure. The crew is at maximum distance from Earth. The communication delay is at or near its worst. The routine has become grinding, and the return journey has not yet begun. Mission planners take this seriously. Crew selection protocols for Mars missions will likely include extensive psychological screening, team compatibility assessment, and training in conflict resolution and stress management techniques that go far beyond what is required for station crews. But no amount of screening can eliminate the fundamental reality. The crew will be alone with each other for years, in a confined space, under constant stress, with no option to leave, and no ability to receive timely help from home. Some friction is inevitable. Some psychological deterioration is probable. The question is not whether the crew will struggle. It is whether the mission can be designed to keep that struggle within survivable bounds. Now, let us add another dimension to the danger. Power. At Earth distance from the Sun, approximately 1 astronomical unit. The solar irradiance at the top of the atmosphere is roughly 1,360 watts per square meter. That is the energy budget that solar panels on satellites and the space station work with. It is abundant. Panels of modest size can generate enough electricity to power complex spacecraft and habitats. Mars orbits at roughly 1.5 astronomical units from the Sun. Apply the inverse square law, which governs how light intensity decreases with distance from a source, and you find that Mars receives approximately 43% of the sunlight that Earth does. That is a significant reduction, but it is not catastrophic. Solar panels on Mars can still generate useful power, though they need to be substantially larger than their Earth orbit equivalents to produce the same output. The Perseverance rover does not use solar panels because NASA chose a multi-mission RTG for its power supply, but the earlier Spirit and Opportunity rovers operated on solar power for years. Opportunity, which landed in January of 2004, survived on solar power for over 14 years before a global dust storm in 2018 coated its panels so thoroughly that it could no longer generate enough electricity to function. Dust accumulation is a persistent threat to solar power on Mars. Martian dust storms can reduce sunlight at the surface by more than 90% during severe events, and fine dust settles on solar panels and stays there unless physically removed or blown off by wind. For a crewed Mars habitat, power demands would be vastly greater than anything a rover requires. Life support systems, heating, cooling, water recycling, air processing, lighting, communications, food production, medical equipment, computing, and scientific instrumentation all draw continuous power. A crewed Mars base would need kilowatts of continuous electrical output, not the hundreds of watts that a rover draws. Achieving this with solar panels alone would require arrays covering hundreds of square meters. And those arrays would be vulnerable to the same dust storms that killed Opportunity. Any serious crewed Mars architecture includes nuclear power as a primary or backup source, most likely a small fission reactor or an array of RTGs, because solar alone cannot be relied upon for uninterrupted power at Mars distance. But here is the detail that matters for the larger story we are telling. At Mars, the Sun is weaker but still usable. Solar power is diminished but not gone. You can supplement it with nuclear systems and maintain a functional power budget. The challenge is real, but it is solvable with current or near-current technology. The reason this matters is that Mars represents the last point in the outward journey where solar power contributes meaningfully to the energy equation. Beyond Mars, as you push deeper into the solar system, the inverse square law becomes merciless. At Jupiter, about 5.2 astronomical units from the Sun, solar intensity drops to roughly 3.6% of what Earth receives. At Saturn, roughly 9.5 astronomical units, it drops to about 1.1%. At Neptune, about 30 astronomical units, less than 1/10 of 1%. The Sun does not vanish, it remains the brightest object in the sky at all of these distances, but its energy output at the spacecraft's location becomes so feeble that solar panels of any practical size cannot keep a mission alive. Mars is where the sun begins to lose its grip as a reliable power source. It is not yet gone, but the trajectory is clear. Every mile further from the sun reduces the energy available to keep systems running, to keep habitats warm, to keep humans alive. And unlike the communication delay, which imposes a time gap but still allows information to flow, and unlike the launch window constraint, which imposes a schedule but still allows cargo to arrive eventually, the weakening of sunlight with distance is absolute and irreversible for any outward-bound mission. You do not get the light back. You do not outrun the inverse square law. You carry whatever alternative power source you brought with you, and that source is finite and aging from the moment you launch. There is one more danger at Mars that sets it apart from anything closer to Earth and establishes a pattern that intensifies with every additional mile outward. Duration. A round-trip Mars mission using conventional chemical propulsion and Hohmann transfer orbits takes approximately 2.5 to 3 years from launch to landing back on Earth. That is the minimum. It includes roughly 9 months of transit to Mars, 18 months on the Martian surface waiting for the return alignment, and another 9 months of transit home. 3 years during which every system on the spacecraft and habitat must function. 3 years during which every seal, every pump, every circuit board, every pressure vessel, every filtration membrane, every valve, every sensor must continue working or must be repairable with the tools and parts on hand. Spacecraft are tested extensively before launch. Components are rated for specific operational lifetimes. Redundant systems are installed for critical functions, so that if one unit fails, another can take over. But 3 years is a long time for machinery to operate in an environment that includes vacuum, radiation, thermal cycling, vibration during launch and landing, and the corrosive fine dust of the Martian surface. Things break. They break on the International Space Station, which receives regular maintenance and resupply. They broke on Opportunity, which lost the use of its front steering wheels years before it died. They broke on the Curiosity rover, whose wheels developed holes and cracks from driving over sharp Martian rocks. Mechanical systems have finite lives, and 3 years of continuous operation in a hostile environment pushes many components toward the edges of their design envelopes. For a crewed mission, equipment failure is not merely inconvenient, it can be life-threatening. A failure in the water recycling system means the crew is drinking from reserves, and reserves are finite. A failure in the carbon dioxide scrubbing system means the air is gradually becoming toxic. A failure in the heating system on a planet where nighttime surface temperatures can drop below -80 degrees Celsius means the habitat is getting dangerously cold, and the crew must fix these problems themselves, using whatever spare parts they carried and whatever repair skills they possess. Because the nearest hardware store is at minimum 34 million miles away, and will not be sending anything for years. The compounding effect is what makes Mars uniquely dangerous compared to the Moon. At the Moon, the communication delay is negligible. The transit time is 3 days. The mission duration is weeks, not years. If something breaks that cannot be fixed, the crew can abort and come home within days. At Mars, every one of those safety margins has either narrowed dramatically or disappeared. The communication delay prevents real-time help. The launch window prevents emergency resupply. The mission duration means systems must survive far longer. And the distance makes evacuation impossible on any human-relevant timescale. Mars is the boundary, It is the line in the solar system where a mission transitions from being supported by Earth to being fundamentally alone. Below this line, closer to Earth, help is slow but reachable. Advice is delayed but deliverable. Supplies are expensive but sendable. Evacuation is difficult but conceivable. Above this line, farther from Earth, those verbs change. Help is not slow, it is unavailable. Advice is not delayed, it is obsolete by the time it arrives. Supplies are not expensive, they are years away. Evacuation is not difficult, it is physically impossible within any time frame that matters. And here is the uncomfortable truth that most discussions of Mars exploration prefer not to dwell on. Mars is only 1.5 astronomical units from the Sun. It is the fourth planet. It is practically a neighbor. Everything we have described, the communication delay, the launch window isolation, the medical autonomy, the weakening solar power, the system endurance requirements, the psychological strain of years-long separation from home, all of this kicks in at a distance that, by solar system standards, is modest. Mars is not the deep solar system. Mars is the near edge of the problem, the threshold, the first rung on a ladder where every step up makes every one of these dangers worse by a significant and compounding margin. Jupiter is not 1.5 astronomical units from the Sun. It is 5.2. Saturn is 9.5. Neptune is 30. The Voyager probes are past 170. And the nearest star, Proxima Centauri, is over 268,000 astronomical units away. At Mars, Earth becomes a delayed advisor. At Jupiter, Earth becomes an afterthought. At Saturn, a fading whisper. At Neptune, barely a signal. And beyond Neptune, Earth becomes something a spacecraft used to know. The Sun is still visible from Mars. The sky is still recognizably a sky. The delay is painful, but the link to home is real. All of that is about to change because we are about to cross into the territory where the Sun stops being a power source, where communication delay stretches from minutes into hours, where radiation belts grow violent enough to damage electronics within days, and where the phrase "no rescue" does not describe a worst-case scenario. It describes the baseline operating condition. The outer solar system does not welcome visitors, and nothing about it gets easier the farther you go. At a certain distance from the Sun, a line is crossed that no amount of engineering cleverness can reverse. It is not a sharp boundary, not a wall you hit, but a gradient that tips past the point of usefulness. Somewhere between the orbit of Mars and the orbit of Jupiter, solar panels stop being a viable power source for any spacecraft doing serious work. The sunlight is still there. Photons are still arriving, but they arrive so thinly spread across so much space that collecting enough of them to keep a mission alive requires panel surfaces so enormous, so fragile, and so heavy that the engineering becomes absurd. By the time you reach Jupiter, 5.2 astronomical units from the Sun, the sunlight hitting your spacecraft has fallen to roughly 3.6% of what it was at Earth. Imagine standing under a spotlight and then backing away until the light on your skin is barely perceptible. That is the Sun at Jupiter. It is visible. It is recognizable. But its energy is a ghost of what it was. NASA proved this was not an absolute barrier when it sent Juno to Jupiter on solar power, arriving in 2016 with arrays spanning roughly 29 feet on each of 3 wing-like arms. Those arrays covered an area of approximately 60 square meters, the largest solar panels ever used on an interplanetary mission. And at Jupiter they generated only about 500 watts. For reference, That is roughly enough to run 5 household light bulbs. Juno made it work because it was an orbiter with a narrow mission profile and modest power demands. But 500 watts from 60 square meters of cutting-edge solar cells at Jupiter tells you everything you need to know about the economics of solar power this far from the sun. A crude habitat with life support systems, heating, communications, food production, water recycling, and medical equipment would demand tens of kilowatts of continuous output. Generating that from solar panels at Jupiter distance would require arrays measured not in tens of square meters, but in thousands. Structures so vast and so vulnerable that any realistic mission architecture rules them out. Solar power as a primary energy source is finished at Jupiter. Beyond Jupiter, it is not even worth discussing. This means that any mission to the outer solar system depends entirely on nuclear power, not as a supplement, not as a backup. As the only source of electricity that keeps the lights on, the computers running, the heaters working, and the instruments alive. And nuclear power in deep space does not mean the compact fission reactors you might imagine. No deep space mission has ever carried a fission reactor. What they carry are radioisotope thermoelectric generators, RTGs, devices that convert the heat from decaying plutonium-238 into electricity through a principle called the Seebeck effect. The plutonium decays naturally, emitting alpha particles that heat the surrounding material. That heat passes through an array of thermocouples, paired metals, that generate a small electric current when one side is hot and the other side is cold. No moving parts, no turbines, no pumps, nothing to jam or wear out mechanically. RTGs are among the most reliable power sources ever built for any application, and that reliability is the only reason humanity has any presence at all in the outer solar system. But RTGs have a fundamental limitation that no design revision can eliminate. They run down. Plutonium-238 has a half-life of approximately 87.7 years. That means every 88 years, half of the remaining fuel has decayed. This sounds like it would provide centuries of useful power, and in theory, the fuel itself lasts a very long time. But the thermocouples degrade independently of the fuel. The temperature difference across the thermocouples, which is what drives the current, decreases as the hot side cools, and the cold side is influenced by waste heat within the generator housing. Over time, the electrical output drops even faster than the raw thermal output of the plutonium. A fresh multi-mission RTG produces approximately 110 watts at launch. Each year, both the fuel decay and the thermocouple degradation combine to reduce the output by roughly 4 watts. After a decade, the generator that started at 110 watts is producing around 70. After 2 decades, it is closer to 30. After 3 decades, it may struggle to produce 20. The Voyager spacecraft are the most vivid demonstration of what this means in practice. Launched in 1977, each Voyager probe carried 3 RTGs that together produced about 470 watts at launch. Nearly 50 years later, that output has fallen to roughly 220 watts, less than half the original capacity. 220 watts is not enough to run all of the probe's original instruments simultaneously. It is not enough to run most of them. NASA has spent years making agonizing decisions about which instruments to shut down and which to keep alive, trading science for survival in a slow, deliberate retreat from capability. In February of 2025, NASA shut down Voyager 1's cosmic ray subsystem, the very instrument that had helped confirm the spacecraft's crossing into interstellar space a decade earlier. In March of 2025, they shut down Voyager 2's low-energy charged particle instrument. Only 2 functioning science instruments remain on Voyager 1. Voyager 2 retains 3, though one of those is scheduled for shutdown within the year. The heaters that once kept fuel lines and sensitive electronics warm have been turned off. The cameras were shut down decades ago. The tape recorders are off. System after system has been sacrificed to keep the core functions alive for just a few more years. This is not a failure of engineering. It is the physics of entropy expressed in watts. The RTGs are performing exactly as predicted. Their decline was calculated before launch and budgeted into every phase of the mission plan. What it illustrates is that nuclear power in deep space is not a permanent solution. It is a slowly shrinking budget. Every year, the spacecraft has less electricity to work with. Every year, it must choose between functions. Eventually, the budget reaches 0, and the spacecraft goes silent. Not because anything broke, not because something collided with it, or because a circuit failed. Because the power simply ran out, the way a flashlight dims and dies when the batteries drain, except that there is no one within 1 billion miles who can replace them. For any hypothetical crewed mission to the outer solar system, this power trajectory would not merely constrain the science program, it would constrain survival. Life support systems require continuous power. Air processing, water recycling, temperature regulation, lighting, communication, navigation, all of these draw from the same finite electrical supply. A crewed vehicle operating on RTGs would need to carry a substantial array of them, far more than any robotic probe has ever used, and would need to plan every phase of the mission around the predictable decline curve of its power supply. Systems that are essential in year 1 might need to be rationed in year 5 and shut down entirely in year 10. The mission duration would be limited not by fuel for propulsion or food for the crew, but by the watt-by-watt exhaustion of the only source of electricity on board. And while the power fades, the radiation intensifies. Jupiter's magnetic field is the strongest of any planet in the solar system. It is approximately 20,000 times more powerful than Earth's and extends millions of miles into space, creating a magnetosphere so vast that if it were visible to the naked eye, it would appear larger than the full moon in Earth's sky. This enormous magnetic field traps charged particles from the solar wind, from volcanic emissions off the moon Io, and from other sources, concentrating them into radiation belts that dwarf anything near Earth. The inner radiation environment around Jupiter is so intense that it can deliver a lethal dose to an unshielded human being in a matter of hours. When NASA sent the Galileo spacecraft to orbit Jupiter in 1995, the probe operated for nearly 8 years, but its electronics suffered cumulative radiation damage that degraded performance throughout the mission. The tape recorder that stored data before transmission to Earth malfunctioned repeatedly. Some instruments lost sensitivity. Circuit boards accumulated ion damage that caused intermittent errors. Galileo was designed to tolerate this, with radiation-hardened components and redundant systems. But even hardened electronics have limits. The probe absorbed a total radiation dose estimated at several 100,000 raids over its mission. Hundreds of times the lethal dose for a human being. When Juno arrived at Jupiter 20 years later, it carried a titanium radiation vault, a shielded box weighing about 400 pounds that enclosed the spacecraft's most sensitive electronics. The Volt reduced the radiation reaching the instruments by a factor of roughly 800. Even so, Juno's orbit was deliberately designed to minimize time spent in the most intense radiation zones. Diving close to Jupiter's cloud tops where the magnetic field lines converge and the trapped particle density is somewhat lower, then swinging far out on long elliptical loops to reduce cumulative exposure. The primary mission was originally planned for roughly 33 science orbits. The science return has been extraordinary, but the radiation toll on the spacecraft systems is real and accumulating. Each pass through the inner magnetosphere deposits more ionizing energy into the electronics, slowly chipping away at the margins of survivability that the titanium Volt provides. For a crewed spacecraft, Jupiter's radiation environment would be one of the most formidable challenges in the entire solar system. A crew approaching the Jovian moons, where many of the most scientifically compelling destinations lie, would be immersed in a radiation field strong enough to cause acute radiation sickness within days without massive shielding. Europa, the ice-covered moon that may harbor a liquid ocean beneath its surface, orbits deep within Jupiter's radiation belts. A surface mission to Europa would expose astronauts to roughly 540 rem per day, enough to incapacitate a human being within hours and kill within days. Operating on or near Europa would require shielding of a thickness and density that would make the habitat enormously heavy. Or it would require extremely short surface stays, measured in hours rather than days, with crews rotating in and out from a shielded vehicle parked in a lower radiation orbit. Neither option is simple, neither is cheap, and both add mass, complexity, and risk to a mission that is already operating at the ragged edge of feasibility. Saturn is kinder in terms of radiation, but crueler in almost every other respect. Its radiation belts are less intense than Jupiter's, though still significant, but Saturn is 9.5 astronomical units from the Sun, nearly twice as far as Jupiter. Sunlight at Saturn has dropped to roughly 1.1% of what it provides at Earth. The average surface temperature of Saturn's largest moon, Titan, the only moon in the solar system with a thick atmosphere, is approximately minus 179 degrees Celsius. At these temperatures, water ice is as hard as granite. Methane exists as a liquid, forming rivers and lakes on Titan's surface. The cold is not merely uncomfortable, it's an engineering adversary that attacks every material and every mechanism on the spacecraft. Metals become brittle at extreme low temperatures. Lubricants designed for terrestrial or near-Earth applications can thicken, freeze, or lose their function entirely. Seals contract and can allow minute leaks that, over months and years, become significant. Electronic components behave differently at cryogenic temperatures, with resistance values shifting, capacitors losing performance, and solder joints becoming vulnerable to thermal stress cracking. The spacecraft's thermal control system, which in the inner solar system primarily deals with shedding excess heat from the sun and from internal electronics, now faces the opposite challenge. It must conserve every watt of heat generated by the RTGs and the electronics themselves, distributing warmth precisely to keep fuel lines from freezing, batteries from failing, and instruments from drifting out of calibration. Thermal blankets, heater strips, and insulation become as critical as the propulsion system. Lose thermal control and the spacecraft does not overheat. It freezes. Valves lock, fuel lines clog, batteries refuse to discharge, and the failure cascade begins. Communication from Saturn takes between 68 and 95 minutes each way, depending on the orbital positions of the two planets. A round-trip exchange takes more than 3 hours in the best case. Every command sent to a spacecraft at Saturn was drafted based on information that is already over an hour old when it arrives, and the response, whatever the spacecraft does in reaction to that command, will not be known on Earth for another hour after that. At Jupiter, the delay was 33 to 54 minutes each way, already far beyond real-time interaction. At Saturn, the delay is large enough that the concept of mission control as a decision-making partner becomes almost fictional. The ground team can plan, they can advise, they can analyze data that has already arrived, but they cannot react to anything. Reaction requires immediacy, and immediacy has been gone since Mars. The Cassini mission, which orbited Saturn from 2004 to 2017, operated under exactly these constraints for 13 years. Every maneuver, every orbit adjustment, every close flyby of Titan or Enceladus or the rings was pre-planned, uploaded as a command sequence, and executed autonomously by the spacecraft. Mission controllers could monitor the results only after the fact, with the full delay baked into every observation. When Cassini made its final dive into Saturn's atmosphere in September of 2017, the signal confirming the spacecraft's destruction took 83 minutes to reach Earth. For 83 minutes after Cassini had already burned up and ceased to exist, the team at JPL did not know whether the maneuver had executed correctly or whether something unexpected had happened. They waited, watching screens that showed data from the recent past, unable to influence an event that was already over. For a crewed mission at Saturn's distance, this delay means that any emergency is handled entirely by the crew, or not handled at all. A hull breach, a fire, a medical crisis, a system malfunction, all of it must be diagnosed, decided upon, and resolved before Earth even learns it occurred. The crew is not just far from home, they are operationally independent in the deepest sense. Their survival depends entirely on their own competence, their own judgment, and the reliability of systems that have now been operating continuously for years. And this is where the compounding nature of deep space danger becomes its most insidious. At Mars, the dangers were severe but somewhat distinct. Communication delay was a problem. Launch windows were a problem. Power reduction was a problem. Medical isolation was a problem. Each one could be described and addressed somewhat independently. By the time a mission reaches Saturn, these problems are no longer separate. They are layered on top of one another, interacting in ways that multiply the risk beyond what any single factor would produce alone. Consider a scenario. A critical pump in the water recycling system fails aboard a crewed spacecraft in orbit around Titan. The crew identifies the failure. They consult their onboard documentation and attempt a repair using spare parts carried from Earth. The repair requires a specific replacement valve. They locate the valve in the spare parts inventory. But when they attempt to install it, they discover that the valve's rubber seal has hardened and cracked. Not from a manufacturing defect, but from years of exposure to the ambient radiation environment inside the spacecraft. Galactic cosmic rays which penetrate the hull continuously and which no practical amount of shielding fully stops, have been slowly degrading polymer materials throughout the vessel since launch. The seal that was tested and certified on Earth 6 years ago is no longer functional. Now the crew must improvise. They need to fabricate a replacement seal or find an alternative material that can serve the same purpose. This requires manufacturing capability and materials that may or may not be available on board. Meanwhile, the water recycling system is offline. The crew is consuming stored water reserves, which are finite. They send a message to Earth describing the situation and requesting advice. That message takes 80 minutes to arrive. Earth's engineers review the situation, consult with materials specialists, and draft a response. That response takes another 80 minutes to travel back. Nearly 3 hours have passed. The crew has been working the problem the entire time, because they cannot afford to wait. By the time Earth's advice arrives, the crew has either solved the problem or has moved on to a different approach. The advice may still be useful, or it may be based on assumptions that have already been overtaken by events. This compound failure, a mechanical breakdown caused by radiation-induced material degradation, complicated by the absence of replacement parts, compounded by a communication delay that prevents timely guidance from Earth, is not a freak accident. It is the predictable consequence of operating complex systems for years in an environment that attacks every material, every component, and every margin simultaneously. And it is not the only such scenario. There are hundreds, thousands. Every system on the spacecraft is aging. Every polymer is absorbing radiation. Every mechanical joint is accumulating wear. Every electronic component is experiencing gradual degradation. The crew is managing not one emergency at a time, but a slowly rising tide of minor failures, each one solvable in isolation, but collectively consuming more and more of the crew's time, expertise, and dwindling spare parts inventory as the mission wears on. Navigation adds yet another layer. In the inner solar system, spacecraft navigate using a combination of star trackers, inertial measurement units, and radio tracking from Earth. The Deep Space Network, NASA's array of large dish antennas located in Goldstone, California, Canberra, Australia, and Madrid, Spain, can measure a spacecraft's distance and velocity with extraordinary precision by timing radio signals. This technique, called radiometric tracking, works well when the spacecraft is close enough to Earth for the signal to be strong and the delay to be manageable. At Saturn's distance and beyond, the signal is weaker. The delay is longer. The tracking updates are less frequent because the Deep Space Network has limited capacity and must share time among every active mission. Errors in position and velocity estimates grow with distance. A small inaccuracy in the spacecraft's known position at Jupiter might mean a discrepancy of a few kilometers. The same percentage of uncertainty at Neptune, roughly 30 astronomical units from the Sun, translates to a discrepancy of tens or hundreds of kilometers. And if a course correction is needed, the delay in commanding that correction means the spacecraft has traveled further along the wrong path before the fix can be applied. Voyager 2's flyby of Neptune in August of 1989 remains the most dramatic demonstration of what navigation looks like at outer solar system distances. The spacecraft had been traveling for 12 years. It was approaching a planet roughly 2.8 billion miles from the Sun, aiming for a corridor in space so narrow that mission planners compared it to sinking a golf putt from across the length of the United States. The flyby was not a simple pass. It was a precisely choreographed sequence designed to carry the spacecraft close enough to Neptune to study its atmosphere and rings, then redirected downward through the orbital plane to pass within roughly 25,000 miles of the moon Triton, the mission's final major scientific target. The margin for error on the Triton approach was measured in tens of kilometers and seconds of timing. Too far, and the science return would be degraded. Too close, and the spacecraft risked collision with debris or gravitational disruption of its trajectory. Every command sent to Voyager 2 during the Neptune encounter took approximately 4 hours and 6 minutes to arrive. Every confirmation of execution took the same time to return. When the spacecraft began its closest approach to Neptune, the sequence had been uploaded hours earlier. The mission controllers at JPL watched the flyby unfold on their screens, knowing that what they were seeing had already happened 4 hours ago. If something had gone wrong, if the spacecraft had entered the wrong orientation, if a thruster had misfired, if the pointing of the scan platform that aimed the cameras had drifted by even a fraction of a degree, there would have been nothing they could do. The error would have played out and concluded long before the signal carrying news of it reached Earth. The team had to trust the navigation solution they had computed, the command sequence they had uploaded, and the spacecraft's ability to execute it flawlessly, with no possibility of real-time correction. It worked. Voyager 2 threaded the corridor, captured stunning images of Neptune's atmosphere and Triton's frozen nitrogen surface, and continued outward. But the success obscured an uncomfortable truth. The entire encounter depended on calculations made days in advance and executed without supervision. At Neptune distance, mission control does not control. It watches history arrive. For robotic probes, this is manageable. Navigators on the ground calculate corrections, upload them, and the spacecraft executes them hours later. The margins are tight but workable. For a crewed mission traveling to a specific destination in the outer solar system, navigation drift becomes a more pressing concern because the crew may need to make real-time adjustments during critical phases, orbital insertion, moon approach, or landing. These maneuvers have narrow windows and little tolerance for error, and they must be executed by people who may not have access to the full navigational infrastructure that a mission closer to Earth would enjoy. Now let us push to Neptune, roughly 2.8 billion miles from the Sun, and observe what has happened to every safety margin we catalogued at Earth orbit. Communication delay at Neptune ranges from approximately 4 to 4.5 hours each way. A round-trip message exchange takes 9 hours at best. You could send a distress call in the morning and not receive a response until evening. And that response would be based on a situation description that was already 9 hours old. For any practical emergency, this is indistinguishable from having no communication at all. The signal still travels. Data still flows. But the latency is so extreme that the information is archaeological by the time it arrives. Earth can reconstruct what happened. It cannot influence what is happening. Solar power is non-existent as a practical energy source. The sun delivers roughly 1/9 of 1% of the energy it provides at Earth. The only illumination is starlight and the faint glow of a sun that appears as a very bright star, brilliant enough to cast faint shadows, but too dim to warm anything, too weak to power anything, too distant to feel like the center of a solar system that still technically bears its name. The spacecraft's RTGs, if they were fresh at launch, have now been operating for years. Every year, 4 fewer watts. The power budget that once seemed comfortable is now a discipline of hard choices. Systems that were considered essential at the start of the mission may have been shut down. Backup systems that were held in reserve may have been activated to replace primary systems that failed. The reserves are thinner. The margins are tighter. Every decision about which instrument to run, which heater to leave on, which computer to keep active is a negotiation between what the mission needs and what the physics of radioactive decay still permits. The thermal environment is severe. Surface temperatures on Neptune's moon Triton reach approximately minus 235 degrees Celsius, making it one of the coldest measured surfaces in the solar system. At these temperatures, nitrogen freezes solid. The engineering challenges of keeping a spacecraft or habitat functional in this cold are extreme, not because any single component fails immediately, but because every component is stressed, and the stress accumulates, and the power available to fight the cold is diminishing every year. Radiation exposure has been continuous since the crew left Earth's magnetosphere years ago. Galactic cosmic rays do not diminish with distance from the sun. They are a feature of interstellar space, and the farther you travel from the sun, the less the solar wind does to deflect them. Beyond roughly 100 astronomical units, where the solar wind weakens to the point that it can no longer hold back the interstellar medium, galactic cosmic ray flux actually increases. But even at Neptune, the cumulative dose from years of unshielded exposure to galactic cosmic rays is biologically significant. DNA damage accumulates, cancer risk climbs, central nervous system effects, including potential cognitive impairment, become a genuine concern for any crew that has been in deep space for years. And repair is the quiet crisis underlying everything else. Every component on the spacecraft was manufactured on Earth. Every bolt, every circuit board, every sensor, every valve was designed, tested, and installed by engineers who understood the system intimately. Those engineers are billions of miles away. The documentation they wrote is on board, stored in computers powered by the same decaying RTGs. But documentation is not expertise. Reading a manual about how to repair a malfunctioning thruster valve is not the same as having repaired one before, and the crew, however well trained, however carefully selected, cannot carry the depth of specialized knowledge that a planetary civilization distributes across thousands of institutions and millions of professionals. They know their systems well. They trained for years, but there will be failure modes they did not train for, because no training program can anticipate every way a complex system can degrade over a decade of operation in an environment it was never biologically or industrially evolved to withstand. The spacecraft, by the time it reaches Neptune distance, is no longer the vehicle that left Earth. It is older. Its systems are worn. Its power supply is diminished. Its materials have been subtly altered by years of radiation and thermal stress. Its crew, if it carries one, is experienced but fatigued, resourceful but stretched thin. And Earth, the origin, the manufacturer, the designer, the repository of every answer to every technical question, is a 9-hour signal delay away, unable to intervene in any crisis faster than the crisis itself unfolds. What has happened between low Earth orbit and Neptune is not a single dramatic escalation. It is a slow, methodical subtraction. Communication went from instantaneous to delayed to functionally absent. Power went from abundant to constrained to desperately rationed. Rescue went from hours away to years away to physically impossible. Repair went from routine to difficult to dependent entirely on what was packed before launch. Radiation shielding went from Earth's magnetosphere to a spacecraft hull to nothing adequate. Thermal stability went from managed to critical to a constant battle against cold that the power budget can barely sustain. Each of these losses happened at a different distance. Each one crossed its own threshold at its own point in the journey outward. But by Neptune, They have all crossed. The spacecraft is operating in a condition where every safety margin that existed in low Earth orbit has been removed or reduced to a sliver. It is surviving on stored reserves, aging systems, and the skill of whatever crew or software is managing the mission. And it is still inside the solar system, still technically within the sun's gravitational domain, still within the range, if barely, of the Deep Space Network's giant antennas. Beyond Neptune, the losses continue. The sun grows fainter, the signal grows weaker, the RTGs continue their slow decay, the cold deepens, the cosmic ray flux increases, and Earth becomes not a partner, not an advisor, not even a distant voice offering comfort. Earth becomes a point of light in the rear view, sending messages that arrive tomorrow about problems that happened yesterday. That is where we are going now. Past the planets, past the heliopause, into the space between the stars, where the last connection to home finally thins to nothing, and the spacecraft discovers what it truly means to be alone. Somewhere past the orbit of Neptune, in the cold dark beyond the last planet, there are 5 objects made by human hands still moving outward. Pioneer 10, launched in 1972, now silent, its transmitter dead since 2003, drifting without voice at an estimated 135 astronomical units from the Sun. Pioneer 11, also silent since 1995, somewhere in the opposite direction. New Horizons, launched in 2006, currently about 64 astronomical units out in the Kuiper Belt, recently awakened from 321 days of hibernation, the longest sleep in its mission's history. Its RTG still producing enough power to run 3 instruments and a radio. And the 2 Voyagers. Voyager 2, at approximately 143 astronomical units, operating with a handful of instruments on a power supply that loses 4 watts every year. And Voyager 1, the farthest human-made object in existence, now approximately 173 astronomical units from Earth, traveling at about 17 kilometers per second, approaching a milestone that captures in a single number everything this story has been building toward. In November of 2026, Voyager 1 will reach a distance of 1 light day from Earth. A signal sent from the Deep Space Network's antennas will take 24 hours to arrive. The spacecraft's response, if it sends 1, will take another 24 hours to return. A full 2-day round trip for a single exchange of information. 2 days between a question and its answer. 2 days between a command and confirmation that it was received. 2 days during which anything could happen aboard that spacecraft, and Earth would not know. 1 light day is not a meaningful boundary in physics. Space does not change at that distance. The interstellar medium does not thicken. No new danger activates, but as a measure of isolation, it is profound. If Voyager 1's computer malfunctioned right now, the engineers at JPL would not learn about it until tomorrow, and the fix they uploaded would not arrive until the day after. For 2 full rotations of the Earth, the spacecraft would be alone with its problem, running on whatever autonomous routines it had been given, unable to call for help in any time frame that resembles urgency. And Voyager 1 has already demonstrated what this isolation looks like in practice. In late 2023, the spacecraft began transmitting gibberish. Instead of coherent science and engineering data, it sent a repeating pattern of 1s and 0s that carried no usable information. The signal was strong. The spacecraft was clearly alive and pointing its antenna at Earth, but the data made no sense. Something had gone wrong inside the flight data subsystem, a computer built with technology from the early 1970s, containing about 69 kilobytes of memory, roughly 1/60,000th the capacity of a modern smartphone. The diagnosis took weeks. The team at JPL had to work with a round-trip communication delay of nearly 46 hours. Every test command they sent took almost a full day to arrive. Every response took almost a full day to return. The engineers could not simply log in remotely and inspect the software. They had to send carefully constructed diagnostic queries, wait 2 days for answers, analyze the results, formulate the next query, and wait again. Each cycle consumed 2 days of real time for a single step in the troubleshooting process. A problem that a technician with physical access to the hardware might resolve in an afternoon stretched across months. The team eventually traced the issue to a corrupted memory chip in the flight data system. They devised a workaround that redistributed the affected code across other sections of the computer's limited memory, uploaded the patch in stages, and by April of 2024, Voyager 1 was transmitting coherent data again. It was a remarkable feat of remote engineering performed across a communication gap of nearly 2 light days round trip. And it illustrated, with painful clarity, how profoundly distance transforms every technical problem from something solvable into something that requires patience on a scale most people have never had to exercise. New Horizons, at 64 astronomical units, faces its own version of this isolation, though it is closer and the delay is shorter. When the spacecraft woke from hibernation in June of 2026, the confirmation signal took 8 hours and 52 minutes to reach mission control at the Johns Hopkins Applied Physics Laboratory in Maryland. Nearly 9 hours. The team had uploaded the wake-up commands almost a year earlier, in July of 2025, before the spacecraft entered its longest sleep. They programmed the onboard computer with a date and time to reactivate, and then they waited. For 321 days, the spacecraft was in a low-power state, running only essential monitoring systems, sending brief weekly health beacons that each took nearly 9 hours to cross the gap. The team could confirm the spacecraft was alive, but they could not interact with it in any meaningful way. They had to trust the hardware, trust the software, trust the design, and wait. When the wake-up confirmation finally arrived, the mission operations manager reported that every weekly beacon during the hibernation had come back green. The spacecraft was healthy. Its instruments were intact. Its RTG, while continuing its slow decline, still had enough output to support the planned science observations. But the margin was visibly thinner than it had been even a few years earlier. Power management has become a dominant concern. Every observation, every data transmission, every heater activation is weighed against the remaining watt budget. New Horizons is not dying, but it is aging. And the arithmetic of its remaining capability is governed by the same physics that is slowly silencing the Voyagers. These 5 outbound machines are the only direct evidence humanity has about what happens to technology in deep space over decades. And what happens is exactly what the physics predicts. Power decays, components degrade, materials weaken, communication becomes more difficult, and the spacecraft grows more alone with every passing year, every added astronomical unit, every additional hour of signal delay. No single catastrophe strikes. The decline is gradual, systemic, and relentless. It is the accumulation of small losses over long periods, each one manageable in isolation, collectively converging towards silence. And they have all crossed or are approaching a boundary that matters enormously for the story of deep space danger: the edge of the heliosphere. The sun does not simply emit light, it emits a continuous outflow of charged particles called the solar wind, a stream of protons and electrons that flows outward in all directions at several hundred kilometers per second. This solar wind inflates a vast bubble in the surrounding interstellar medium, a region called the heliosphere. Inside this bubble, the sun's influence dominates. Its magnetic field, carried by the solar wind, fills the space between the planets and provides a partial shield against the galactic cosmic rays that stream through the galaxy from supernova remnants and other violent sources. The shielding is not complete. Galactic cosmic rays still penetrate the heliosphere, but the solar wind deflects and moderates the incoming flux, reducing the intensity that reaches the inner solar system. At a certain distance, the solar wind slows, compresses, and eventually stops. It encounters the pressure of the interstellar medium, the thin gas and dust that fills the space between stars, and it cannot push any farther. This boundary occurs in stages. First, the termination shock, where the solar wind abruptly slows from supersonic to subsonic speed. Then, the heliosheath, a turbulent region where the slowed solar wind piles up and mixes with interstellar particles. And finally, the heliopause, the outermost edge, where the solar wind's pressure balances the pressure of the interstellar medium and the sun's direct influence effectively ends. Voyager 1 crossed the heliopause in August of 2012, approximately 122 astronomical units from the Sun. Voyager 2 crossed it in November of 2018 at approximately 119 astronomical units. Both spacecraft detected a dramatic change in the particle environment. Inside the heliosphere, the instruments measured a mixture of solar wind particles and a reduced flux of galactic cosmic rays. Outside, the solar wind vanished, and the galactic cosmic ray intensity increased sharply. The spacecraft had left the sun's protective bubble and entered interstellar space. For any future mission, crewed or robotic, traveling beyond the heliopause, this crossing marks the point at which the last natural shield between the spacecraft and the full intensity of the galactic radiation field is gone. Inside the heliosphere, the solar wind provides a modest but real reduction in cosmic ray exposure. Outside it, the spacecraft receives the unattenuated galactic cosmic ray flux, the same radiation that fills the entire galaxy, generated by events hundreds or thousands of light years away, arriving from every direction, every second, forever. There is no cyclical relief. There are no seasons. The flux does not decrease with distance because the spacecraft is no longer moving away from the source. The source is the galaxy itself, and the spacecraft is inside it. For a hypothetical crewed interstellar mission, the radiation exposure beyond the heliopause would be cumulative, continuous, and essentially permanent for the duration of the voyage. Every day adds to the total dose. Every month increases the statistical risk of cancer, cardiovascular damage, and central nervous system effects. Every year pushes the crew further into territory where the long-term biological consequences of radiation exposure are not merely possible, but probable. And the mission cannot turn around. It cannot seek shelter. The nearest magnetic shield, Earth's magnetosphere, is years or decades of travel behind them. The crew absorbs the dose and lives with the consequences, whatever those turn out to be. And now consider what else has been lost by this point in the outward journey. The sun, which dominated the sky in the inner solar system, has diminished to a very bright star. At 100 astronomical units, it is still the brightest object in the sky by an enormous margin, roughly 1,000,000 times brighter than the brightest star in the night sky. But it provides no meaningful energy. Its warmth is undetectable. Its gravitational pull is still present, still bending the spacecraft's trajectory into a long hyperbolic arc away from the solar system. But the connection is mathematical, not experiential. The sun does not feel like a sun anymore. It feels like a particularly bright star behind you, and the direction you are going has nothing that bright ahead. Communication has stretched past the point where the word communication accurately describes what is happening. At Voyager 1's current distance, a signal takes nearly 24 hours each way. At double that distance, it takes 2 days each way. At the inner edge of the Oort cloud, a vast spherical shell of icy bodies that is thought to extend from roughly 2,000 to perhaps 100,000 astronomical units from the Sun, the one-way signal delay reaches weeks. At the far edge of the Oort cloud, it reaches more than a year. And Proxima Centauri, the nearest star beyond our own, sits at approximately 268,000 astronomical units. A signal from Proxima Centauri takes 4.24 years to reach Earth. A round-trip exchange takes 8.5 years. At these distances, the concept of mission control ceases to exist in any recognizable form. There is no one to call. There is no help to request. There is no advice that can arrive in time to matter. The spacecraft, or the crew, is entirely self-reliant. Every decision, every repair, every navigational correction, every medical intervention, every interpersonal conflict, every mechanical failure must be handled using only the resources and expertise carried on board. Earth is not absent. It is still there, still listening, still transmitting. But its messages arrive from the past, describing a version of the world that has moved on without the crew, and the crew's messages arrive at Earth describing a version of the mission that has already evolved beyond what anyone on the ground can influence. Navigation in this void presents its own quiet crisis. Inside the solar system, spacecraft navigate using radio tracking from the Deep Space Network, combined with star trackers and inertial measurement units. But the Deep Space Network was designed for solar system distances. Its antennas are powerful, but they have limits. At interstellar distances, the signal weakens. The tracking precision degrades. Tiny errors in the spacecraft's known position, measured in fractions of a degree, compound over light years into deviations measured in billions of miles. An interstellar spacecraft would need to perform its own navigation using onboard star trackers, measuring the apparent positions of reference stars and calculating its location from their angular displacement. As the spacecraft moves, the star field shifts due to parallax, the change in apparent position caused by the observer's own motion. This shift must be measured with extraordinary precision and corrected for in the navigation solution. A fraction of a degree of accumulated navigational error over a journey of decades or centuries means missing the destination star system entirely, passing through empty space where the target should have been, continuing onward into the void with no destination ahead and no way back. There is a photograph that captures the emotional reality of all this more powerfully than any number can. On February 14th, 1990, Voyager 1 was approximately 40 astronomical units from Earth, roughly 6 billion kilometers out, heading away from the solar system after completing its tour of the outer planets. At the request of Carl Sagan, NASA turned the spacecraft's camera back toward the inner solar system and took a series of photographs. One of those images showed Earth as a tiny point of light, less than a single pixel in size, suspended in a scattered ray of sunlight. Sagan called it the pale blue dot. From 40 astronomical units, Earth was already almost invisible, a fraction of a pixel in a vast frame of empty black. Everything that has ever happened in human history, every war, every symphony, every birth, every death, every act of love and cruelty and wonder occurred on that speck. And from just 40 astronomical units away, you could barely see it. Voyager 1 is now more than 4 times farther. From its current position, Earth would not register on any camera the spacecraft carries, even if the cameras were still functional, which they are not. Earth is there, but it is lost in the glare and the distance, indistinguishable from the background of stars. Now imagine a crew aboard a vessel that has passed that point. Not a robotic probe carrying cameras and magnetometers, but a crude spacecraft heading outward, away from every planet, away from the sun, toward a destination that is decades or centuries of travel ahead. Imagine what the days feel like. The sun has been shrinking for years. When the mission launched, it filled a viewport with warmth and light that felt instinctive, a connection to every sunrise anyone aboard had ever seen. At Mars, it was smaller, but still recognizably the sun, still bright enough to cast sharp shadows, still warm enough to matter. At Jupiter, it had diminished to something that looked more like a very bright lamp, at a great distance. At Saturn, it was a brilliant point whose warmth the skin could no longer detect. And now, past the heliopause, it is one star among many. Brighter than the rest, yes, but no longer dominant. No longer the center of anything that the crew can feel. They know intellectually that they are still gravitationally bound to it, that they are still inside the Oort cloud, that the sun is still technically their star. But the knowledge is abstract. The felt experience is that they left their star behind somewhere in the outer solar system, and what they see now through the aft viewport is just a memory that has not yet finished fading. The crew has been together for years. They have passed every milestone that the mission plan described. They have celebrated birthdays in a habitat that grows no larger. They have grieved crew members who did not survive the journey, sealed in a storage compartment because there is no soil to bury them in, and no atmosphere to scatter their ashes into. They have repaired systems whose failure modes were not in any training manual. They have made decisions without Earth's input, and lived with the consequences. Some of those decisions were correct, some were not, and the ones that were not cannot be undone, because the only direction the mission moves is forward. The routine has calcified into something that is no longer routine in any comforting sense. It is repetition without variety, discipline without reward, labor without change. The same corridors, the same recycled air with its faint metallic smell that the crew stopped noticing years ago, but that visitors from Earth, if any could arrive, would find immediately unsettling. The same faces across the same table at every meal, the same stars outside the viewport, shifting so slowly against the background that the motion is undetectable from one month to the next. Every day is structurally identical to the one before it. The mission continues not because of momentum in the emotional sense, but because of momentum in the physical one. The spacecraft is moving and it cannot stop. Messages from Earth still arrive. They carry news that feels increasingly foreign. Political events in countries that some of the younger crew members, the ones born after launch, have never seen. cultural references that require explanation, updates about people the crew once knew who have grown old or died. The time lag is now measured in weeks or months. A message sent from the ship on a crew member's birthday receives a reply so far in the future that the birthday has been forgotten by the time the response arrives. The correspondence does not feel like communication anymore. It feels like reading letters from another century, written by people who live in a world the crew can no longer fully imagine. And there is no destination in sight. The nearest star, if that is where they are headed, is still decades away. The arrival, if it comes, will be witnessed by people who are not yet born, children of the current crew or children of those children. The people alive right now on this ship, making these repairs, breathing this air, absorbing this radiation, will not see the end of the journey. They will live and work and grow old inside this vessel. They will maintain it not for themselves, but for people who do not yet exist. And they will do this knowing that they volunteered for it, or that their parents did, and that the decision cannot be reversed. This is the psychology of interstellar travel, not the dramatic loneliness of a single castaway, not the temporary deprivation of an Antarctic winter. A permanent, structural, inescapable condition of being somewhere that is not going to change, heading towards something that is not going to arrive, surrounded by a void that does not care. This is the final condition of deep space, not a dramatic confrontation with a cosmic predator, not a collision with an unforeseen obstacle, not a sudden, cinematic emergency that demands heroism. The final condition is quiet. It is the slow, steady physical reality that every system supporting life and function has been diminishing since the moment the mission left Earth's orbit, and at sufficient distance, the diminishment becomes total. The power is nearly gone. The communication is a ghost of what it was. The sun is a memory. The magnetosphere is a concept from another era. The spare parts are exhausted or degraded. The crew, if there is one, has been absorbing radiation for years or decades. The hull has been absorbing micrometeoroid impacts for just as long. And Earth, the place where all the answers live, the place with the hospitals and the factories and the engineers and the breathable air, is a signal delay so long that by the time a cry for help arrives, the crisis has already ended one way or the other. This is what makes deep space the most frightening environment that exists. Not what inhabits it, not what lurks in the darkness between the stars. The darkness between the stars is, as far as we know, empty. There are no predators, there are no hazards lying in wait. There is nothing dramatic hiding at 50 astronomical units, or 500 or 5,000, that suddenly leaps out and destroys a spacecraft. The environment is passive. It does not attack. It does not malfunction. It does not decide to become lethal. It does not have to. Because distance does the work. Distance removes the communication that lets Earth help. Distance removes the sunlight that provides power. Distance removes the magnetosphere that deflects radiation. Distance removes the rescue capability that could bring a crew home. Distance removes the resupply chain that could replace a broken part. Distance removes the medical infrastructure that could treat a sick crew member. Distance removes the launch windows that could send reinforcements. And distance extends the mission duration, which means every system must survive longer, every component must last further beyond its design life, every material must resist degradation for more years than it was ever tested to endure. Deep space does not kill you with a single blow. It kills you by subtracting everything that keeps you alive, one margin at a time, across millions and then billions of miles, until the machinery you depend on has outlasted its own engineering, and the people you depended on are a day's signal away, and the star you orbited is a bright point behind you, and the only resources you have are the ones you packed before you left. Everything a deep space mission carries was loaded before launch. Everything it will ever have is already on board, and everything on board is aging, decaying, wearing down, running out. The Voyager spacecraft have now been traveling for nearly 50 years. They are humanity's longest-running missions. They have crossed the heliopause, entered interstellar space, and continued transmitting data back to Earth, with systems designed before most of the people reading their data were born. They are engineering triumphs of the highest order, and they are dying. Not because something went wrong, because distance and time are doing exactly what distance and time always do. The plutonium is decaying. The thermocouples are degrading. The instruments are being shut off one by one. The heaters are already gone. The cameras have been dark for decades. Within the next few years, possibly by the end of this decade, the last instruments will fall silent. The transmitters will go quiet. The spacecraft will continue traveling, carrying their golden records, their messages from Earth, their engraved diagrams showing the position of the Sun relative to nearby pulsars. But they will carry all of it in silence, drifting through interstellar space at 17 kilometers per second, unreachable, uncontactable, alone in the most complete sense that any object has ever been alone. And they will still be inside the Oort cloud, still technically within the Sun's gravitational domain, still tens of thousands of astronomical units from the nearest star. The interstellar void is not just large, it is large enough that the fastest objects humanity has ever launched will not cross it within any time frame that human civilization, as it currently exists, is likely to survive to witness. Voyager 1, at its current speed, will take approximately 73,000 years to travel the distance to Proxima Centauri, if it were heading in that direction, which it is not. The scale of interstellar distance does not dwarf the solar system. It makes the solar system, with its planets and moons and asteroid belts and Kuiper belt objects, look like a small clearing in a forest that stretches past the horizon in every direction. And every mile into that forest removes something. First, the ability to talk to home in real time. Then, the ability to receive help within days. Then, the ability to receive help within months. Then, sunlight. Then, the solar wind's radiation shield. Then, navigational certainty. Then, the ability to receive help at all. Then, the ability to be heard at all. Then, the faintest trace of the sun's warmth. And finally, any connection to the place that launched you, beyond a memory encoded in the mission's computers and the minds of the crew. That is the truth at the center of this story. Deep space is not terrifying because it contains something terrible. It is terrifying because it takes away everything familiar. Every light, every voice, every helping hand, every warmth, every margin for error, every second chance. It does this gradually, almost politely, one subtraction at a time, spread across distances so large that the loss is imperceptible on any given day. But the accumulation is relentless, and the destination is always the same. A spacecraft moving through the dark, carrying everything it will ever have, powered by a fuel source that is slowly dying, maintained by systems that are slowly aging, crewed by people, if it carries people, who are slowly absorbing a radiation dose that cannot be reduced and cannot be reversed, heading deeper into a void that offers nothing, provides nothing, and changes nothing about the laws of physics that are quietly, patiently, inevitably consuming every resource the mission carries. The farther you go, the less space has to do. Because distance has already done almost everything. It has removed the communication, it has removed the rescue, it has removed the power, it has removed the shielding, it has removed the resupply, it has removed the ability to call for help and the ability to receive it. And what is left, after all of that is gone, is a spacecraft and the void. And the void is patient, and the spacecraft is not. Every spacecraft humanity has ever sent into deep space has eventually gone silent. Not because something attacked it, not because a dramatic emergency destroyed it, because time and distance consumed every resource it carried, 1 watt and 1 mile at a time, until there was nothing left to consume. That is the fate that awaits every outbound machine. And it is the fate that would await any crew bold enough or desperate enough to follow them. The deepest terror of deep space is not a monster. It is a fact. The farther you travel from Earth, the less you have. And the less you have, the less it takes to end you. Distance is not the road to danger. Distance is the danger. And it has been the danger from the very first mile.